In this lesson, we're diving into the fascinating applications of generative models in natural language processing. Generative models have reshaped how we understand and generate text data, paving the way for tasks once thought to be uniquely human, like writing essays, producing poetry, and even engaging in conversations. So far, we've explored deep learning generative models, particularly Generative Adversarial Networks, or GANs, and variational autoencoders, known as VAEs. We examined their architecture and training processes, implementing them in Python using PyTorch, and discussed their effectiveness in generating realistic data. We even visualized generated images and explored the unique capabilities of each model for different applications. This journey into generative modeling has really set the stage for our further exploration of advanced techniques and their applications. Now, let's talk about how these powerful tools are applied to natural language processing, especially highlighting the impact of models like transformers and BERT. Generative models in NLP have significantly changed the landscape of how machines understand and produce human language, and at the heart of this transformation are advanced architectures like the transformer model. Introduced in the paper "Attention is All You Need," the transformer brought forth the attention mechanism, which allows for better context retention and understanding across long texts. With the transformer, sequential data can indeed be processed in parallel, enabling faster training and more efficient handling of extensive datasets, a real game changer compared to earlier architectures like RNNs, those recurrent neural networks. The displayed pie chart, titled "Performance of Generative Models in Natural Language Processing Applications," presents 4 application categories with hypothetical performance scores: text generation at 95%, dialogue systems at 90%, sentiment analysis at 85%, and summarization at 80%. So, what can we conclude from these proportions? Well, first off, text generation takes the largest slice of the pie. This indicates that generative models excel in producing fluent, coherent text and creative content. Right behind it, we have dialogue systems, which suggests that these models are also highly capable of maintaining context and delivering interactive conversational responses. This high score, you might notice, implies their suitability for applications like chatbots and conversational AI, after some fine-tuning, of course. Now, let's talk about sentiment analysis. While it's typically seen as a discriminative task, it still shows strong performance, reflecting that generative architectures can be effectively adapted for classification-style outputs or even as feature-rich encoders that feed downstream classifiers. And summarization? Well, it takes the smallest share at 80%, hinting that condensing and abstracting content is comparatively more challenging for generative models. Often, this requires specialized training objectives or hybrid extractive-abstractive approaches. Overall, this pattern paints a clear picture. Effectiveness runs from open-ended text production toward tasks demanding precise compression or classification. So, when you're making practical choices, prioritize generative approaches for creative and interactive tasks. And for those areas where performance lags, like summarization, don't forget to plan some additional task-specific strategies, okay? Think data curation, objective engineering, and evaluation metrics, like Rouge and Blue, along with human evaluations, to really fine-tune your approach. Now, let's dive into implementing a self-attention mechanism in our transformer model using Python and PyTorch. We'll kick things off by defining a class called self-attention, which, by the way, inherits from nn.module. In the constructor method, we'll initialize some essential parameters, like the embedding size and the number of attention heads. It's important to check that the embedding size is divisible by the number of heads. Why? Well, this ensures the proper functionality of multi-head attention. Now, moving on to the forward method, we'll process the input tensor, pulling out the batch size and sequence length as we create the necessary representations for values, keys, and queries through linear transformations. After that, we reshape these representations for multi-head processing and permute them to fit the required dimensions. The attention mechanism then computes energy scores by taking the dot product of the queries and keys. We normalize these scores using a softmax function to derive our attention weights. Then, we multiply these attention weights by the values to generate our output for this layer. This enriched output captures the essential information from the input, preparing it for use in subsequent layers of the transformer architecture. And that's how we facilitate the model's ability to efficiently process complex relationships in language. Now, let's see how we can implement a simple transformer model for text generation. The code begins by defining the transformer class, which inherits from nn.module. This is a standard practice in PyTorch for creating neural network models. Inside the constructor, or the _init method, we first create an embedding layer that transforms the input vocabulary into dense vector representations. This layer is super important as it helps the model understand the meanings of words in a continuous space. Next, we instantiate a list of self-attention blocks which we create through a loop that runs for the specified number of layers. This is crucial because each block allows the model to attend to different parts of the input sequence, effectively capturing relationships and dependencies. Finally, after processing through the self-attention layers, the output is fed into a fully connected layer that translates the learned representations into vocabulary probabilities for each word. Now, let's take a look at the forward method, which defines how data flows through the model. When the input passes through the embedding layer, it is then forwarded through each self-attention block sequentially. At the end, the model outputs the predictions, which can be used to generate coherent text when trained on appropriate datasets. Now, let's implement a training loop for our conversational AI model, which will allow the model to learn from the dataset over several epochs. This function, train model, kicks off by setting the model to training mode, preparing it for those important updates. It then iterates through the specified number of epochs, and each epoch represents a complete pass through the dataset. During each epoch, we traverse through the data loader, which feeds input-output pairs to the model. For every batch processed, the optimizer's gradients, listen closely here, are reset to 0 using optimizer.0grad. This step is crucial because we want to ensure that previous gradients do not affect the current updates. Then, the model generates predictions based on the input data. We compute the loss by comparing these predictions with the actual targets, reshaping them appropriately for the criterion we're using. After that, we backpropagate the loss through the model with loss.backward, updating the weights based on how well the model performed. And finally, the optimizer applies those calculated gradients, effectively tuning the model's parameters. Throughout this process, we keep an eye on things by printing the current epoch along with the loss, which lets us monitor the model's learning progress. Once we've defined all the necessary components, we just call this function with our transformer model and other parameters, and voila! The training process is initiated. Now, let's see how we can implement a text summarization algorithm using a pre-trained BART model, which, believe me, is known for its effectiveness in generating concise summaries from longer texts. First, we're going to start by importing the necessary components from the Hugging Face Transformers library. We'll specifically need the BART for conditional generation model and the BART tokenizer. The tokenizer, it's essential for converting input text into a format that the model understands, whereas the BART model is equipped to generate those summaries we want. Now, let's initialize the tokenizer and model with the pre-trained weights from Facebook/BART large CNN, which is, you guessed it, designed for summarization tasks. All right, we're going to define a function called summarize text right now, where we encode our input text prefixed with summarize. This step is crucial as it guides the model on what task we want it to perform. The function specifies settings like max length and truncation. This ensures our input fits perfectly within the model's capacity. Then, with these encoded inputs, we invoke the model's generate method, which produces summary IDs that reflect the condensed version of the input. Finally, we decode these generated IDs back into readable text, stripping away any special tokens as we go, and return that summary. This succinct approach, I promise, drastically simplifies complex NLP tasks, allowing developers like us to focus on building applications rather than getting lost in the intricacies of model training. As we continue exploring the vast capabilities of generative models in natural language processing, we should also consider their applications in creative writing, automated storytelling, and content creation. Tools like AI Dungeon utilize these generative models to craft narratives based on user inputs, dynamically generating plot lines and providing tailored storytelling experiences. This creativity is fueled by the underlying transformers, which enable the AI to maintain consistent story arcs grounded in context. However, ethical considerations are paramount as we leverage these powerful models. While promoting the use of generative models to create compelling narratives, we must remain vigilant about how this technology shapes discourse and the potential for misinformation or biased representations in the content produced. Proper monitoring and responsible deployment of these tools are vital to ensure that they serve a constructive purpose. In summary, generative models have opened the door to innovative applications in natural language processing, impacting everything from chatbots to creative writing. With the power of transformer architectures and the functionality of pre-trained models like BERT and BART, we can harness the ability to generate meaningful text autonomously. The journey through generative models has truly transformed our interactions with machines, making language a domain ripe for exploration and limitless potential. So I encourage you to continue experimenting with these models, dive into the realms of NLP, and see where your creativity takes you. With every step you take in your learning journey, you're contributing to the interplay between human thought and machine-generated insights, paving the way for future advancements in language and beyond.